Okay. XSDs are a treasure of information. And there are great and obvious ways of using XSD information, like document validation, data binding, documentation, communication, covered by great and mature tools. But there is a hidden potential that remains. And today I shall talk about how to start using this potential. First, let me introduce a term. An XSD-based tool, I call a tool treating XSD contents as essential input. So first I shall argue that you might be interested in such tools, developing and using them. But there is a basic problem besetting the development of XSD-based tools. And a clear understanding of this problem leads to a straightforward solution which consists in a novel kind of resource obtained from XSD by a generic transformation. And this new resource provides us with a fresh starting point for developing XSD-based tools. And several examples will demonstrate the new possibilities. Okay, so why should you be interested in XSD-based tools? There are several great tools which we just take for granted. Of course, document validators, then the data binding generators like JAXB, and schema tree viewers like they are offered by IDEs like Oxygen. But the question is if these tools give us everything that XSD has to offer. So let's look or imagine a couple of new tools which you probably have not yet come across. A document-oriented schema diff tool would report the differences between two versions of a schema, not in terms of what has been done to the schema, but in terms of what has changed about the instance documents. What is different about them with a new version? A fact tree writer would analyze a probably large set of instance documents and arrange statistical findings in a tree structure that reflects the tree structure of the instance documents, and thus give you a combined view of model and the actual use of the model. For example, what is the actual use of optional elements and attributes and of various choice branches. And a code generator might take advantage of schema information in order to minimize the effort required to implement document transformations. I am convinced that such tools can give us real value and also that they fill a gap because they accomplish something that simply cannot be accomplished without accessing schema information. So much for the promise. But there is a problem. Why does virtually nobody attempt to write such tools? And there is a plain answer: it's too difficult. And this difficulty has a fundamental reason. Those new tools, I can imagine, they need access to the tree structure of the instance documents. And XSDs describe instance documents which are trees, but schema in itself is not a tree, it's a graph. It's a graph of interrelated components. And this graph nature makes it very, very difficult, if the schema is not trivial, to reconstruct the actual tree structure of the instance documents. Usually it's simply impossible without tools. So this slide summarizes the graph nature of XSD. It's not at all a fault, a design fault of XSD, because this graph structure is exactly what enables reuse of components. For example, a type definition can be used by many attribute declarations, element declarations, but also by other types as a base type, or as an item type, or as a member type, and so forth. So there we have this problem. Schema is as it is. There's a good reason why it is so, but the tree structure of the instance documents is locked away in this graph nature. And now a train of thought. Given in XSD, every valid root element name identifies a document type. And for every document type, the XSD implies a document model. And this document model is definitely tree structured. So consider this solution. Define an XML representation of the document model and provide a generic transformation of arbitrary XSD into its tree structured document models. So the gist of the solution is a new resource obtained from XSD by a generic transformation. It reflects the tree structure of the instance documents. It is tree structured. It is transformation friendly, therefore, and it is meant to be used as an intermediary to be transformed into the ultimate artifacts of interest. Okay. Sorry, don't know why this is cut off. Now it's time to define the document model, and I call it a location tree. Think of location trees as XML equivalents of the graphical schema representation we are used to from IDEs, as shown on this slide. In search of a document model resource, an obvious approach, I think, is to represent the elements and attributes of the document model by XML elements named after the elements which they represent. So this schema representation represents a simple document type with a traveler's root element, one or more traveler children which have a name and an age child, and then a choice of 3 more elements as a third child, and one of these elements has a couple of attributes. So let's also represent these attributes by XML elements, and something like a choice can, of course, also easily be represented by an XML element named choice, but put into a special namespace to avoid confusion with attributes and elements. Well, and what then emerges is a backbone of elements representing the tree structure of the instance documents. So we have elements in this document which represent elements in the instance documents. I call them element locations. And we have elements representing attributes, and they are wrapped in an attributes element to avoid confusion with elements. Further, we have a compositor, a choice, and these location elements representing instance document elements and attributes, they have properties. And this, on this slide, I omitted almost all properties in order to avoid the clutter and to let the structure emerge clearly. So to give you an idea about of the full model, let's look at the properties of an attribute location. And as this slide shows, for example, an attribute location has about a dozen properties represented in our XML document model by attributes attached to the element representing the attribute or element at hand. So for example, we have properties representing cardinality constraints, various type properties, and also something like pointers back to the original source schema in order to align the location tree and the original schema. The full document model also contains supplementary elements which are not part of this backbone giving you the structure. They are used to give additional information about the element and attribute locations which could not be accommodated in attributes. So for example, again, this is an attribute location representing a check status attribute, and it has a user-defined type. And therefore, in the model, there is a child element which gives you a structured representation of the user-defined type to give the user of the model full access to all the information in the schema. And for example, schema annotations are also captured by such supplementary elements. All right, now we can summarize what this is, a location tree. Again, a location tree is an XML representation of a document model as it is implied by the schema. A location tree consists of a backbone, supplementary elements, and property elements. The backbone gives you the structure. It is a tree of elements and attributes, and compositors like choice and sequence. Supplementary elements give you detailed information about simple types and annotations, and they are accommodated as child elements of the respective location elements. And we have property attributes. So I would like to round off your understanding of location trees by taking a closer look at what is this actually an element location. So intuitively, it's immediately obvious it represents an element as it appears in an instance document. But what's the nature of this entity? And in fact, it is a model of XML elements. More precisely, it's a model of all XML elements which appear in a particular document type at a particular place. So all the elements represented by an element location have the same data path. And it is important to understand that every element location can be mapped to an element declaration in the schema, an XS element. And all the properties of a location are just derived from this element declaration, directly or indirectly. And it's also interesting to note that this unambiguous mapping of an element location to an element declaration, the declaration in the source schema, the location in my document model, this mapping cannot be inverted. An element declaration in the schema can be used by many element locations in my model, or perhaps by no element location at all. Therefore, one can regard element locations as the use of an element declaration from the schema in a particular context, a particular place in a particular document. And everything I've said about element locations can be transferred to attribute locations. A few words about compositors. We have three: an alignment with schema, sequence, choice, and all. But sequence is the default compositor, the default group. Sequence elements are left out if the omission does not lose any information. They are not left out in cases where this would distort the information. This is the case if a sequence has a minimum or maximum cardinality which is not 1. Then I must not leave out the sequence element, and I must attach this property, this cardinality information at the sequence element. And likewise, when the sequence is a child of a choice, I must not leave out the sequence element, obviously. And when the location tree is constructed in this process, an operation called group normalization is applied, which normalizes away as many groups as possible, which can be defined by the author, but which are in fact superfluous. For example, pseudo groups with a single member, or nested choices, or nested sequences. They are optimized or normalized away if it's possible without loss of information. Okay, you can use an open source tool available from GitHub in order to transform your XSDs, arbitrary XSDs, into its location trees. Now the question, how to use the location trees. I want to look at a few examples: schema queries, schema reports, fact trees, and metadata trees. Let's start simple. A schema query tool might give you the data path of elements and attributes in the instance documents which match certain conditions. For example, have a certain name or have a certain type or a default type and so on. And such a tool would just have to query the location tree and then map the matching location nodes to data paths. When you have a location tree and you have somehow selected, let's say, an element location or an attribute location, as you remember, this represents elements or attributes found in a particular document type at a particular place. They all have the same data path. What is the data path? This can be obtained by a simple XPath expression applied to this node within the location tree, shown on this slide. So if you have written, for example, as an xquery function, this mapper from location node to data path, then a few lines of code suffice to produce, let's say, an initial version of a schema query tool. This tool would extract from the user a location tree and a name pattern, and it would return all data paths in the documents described by the schema which have a name matching this name pattern. Let me demonstrate. So here I supply to this little tool a location tree obtained for an industry schema from the travel industry, which I obtained for one particular document type. And to start with, I say, well, any name. The name pattern is a wildcard. Give me all data paths which are found in this document type. And then I get almost 2,000 data paths. Okay. Then I say, it's a rather large message. Are there any elements or attributes with a name containing the string, say, insurance? Here we are. So in this really pretty large message, almost 2,000 data paths, I'm informed that there are 3 items which are named somehow insurance something. 1 attribute and 2 elements. Just as a mind game, try to imagine how you would implement this tool without location trees. It is amazing to become aware how you can implement a simple but effective XSD diff tools. Given 2 schema versions, it would give you all data paths added by the new version or removed from the old version. A few lines of code. And it would be a Hercules task to do this without location trees. I do not think yet you could write this in 1 week of full-time work. I do not think. I certainly couldn't. Let me demonstrate. Okay. Here I provide the tool with location trees from an industry schema from 2013 and from 2017. again, this is a huge schema with hundreds of document types, and I produce the location trees only for one document type, which is one web service request, but a large one. So, and the tool tells me that a few paths have been added, and I see the new data paths, and I see that no data paths have been removed. Let's turn to schema reporting. A tree sheet is a novel kind of document model report. It's a text file with a left-hand side depicting the tree structure, and the right-hand side giving you information about the items you see on the left. And the kind of the information shown on the right depends on the type of the tree sheet. So this example shows you on the right-hand side not the name only, but a description of simple data types of which the items on the left hand have. And this next tree sheet shows you the schema annotations which these items have. So this is a very convenient way of looking at the documents defined by your schema. And tree sheets can also represent, on the right-hand side, information which does not stem from the schema, but from other sources, and I will come back to that shortly. A new concept is a location tree model descendant. It's a model which you obtain by taking the backbone of a location tree and attach to it new attributes or child elements giving you information about the items which does not stem from the schema. So it's like a recipe: take the location tree, keep the backbone, throw away all the property attributes and supplementary elements you are not interested in, and attach something new to it. Important use cases are fact trees and metadata trees. A fact tree associates the locations with facts about the items which they represent. So for example, let's say a location represents an optional element, and then a fact about this location would be the fraction of instance documents observed in a sample which do use this optional element. And a values tree associates a location with a sample of data values actually observed in instance documents. And fact trees can be very nicely represented also by tree sheets, and I would like to demonstrate this to you. So this is a tree sheet representation of a fact tree, a frequency tree. The database is a large sample of web service messages sent from one particular client. And this tree sheet shows you the frequency with which the various items in the document model have been used. And the next tree sheet shows you, again, a frequency tree, but it's a different sample of web service messages. It's the messages sent by another client. So we can observe here very conveniently how the two clients have different patterns of using our web service interface. And similarly, here we have a values tree. We see the actual data values observed in instance documents, or in this case, web service messages. Here the values received from client 1. Here the values received from client 2. And I think it's an interesting experience to open several tree sheets in an editor, as I do here, and switch between the tabs, because this gives you an experience of looking at this complex data structure from different sides and perceiving different aspects. So, and you could, of course, also again return to the conventional tree sheets, giving you tree type descriptions, annotations, and so I think this is quite interesting, especially because you perceive the message as a whole. You do not receive message about one item, but you see the message as a whole. The final example of using location trees touches upon metadata trees. And as an introduction, please consider a transformation between two document types. This slide shows, so we have passengers and passenger elements to be transformed into travelers and traveler elements. And if you use xQuery, you can write transformation code which is amazingly clear, readable, and intuitive. And as a matter of fact, what you see here is the transformation code, and the transformation code looks quite similar to the instance document, or in other words, to the model of the instance document. Observe. It's quite similar. Taking a closer look, you might perceive that the code of this transformation could be read as an XSD-derived scaffold of code into which expressions are embedded. XSD-derived means this scaffold of code, shown here in brown, is completely independent on this source document type. It's just determined by the target document type. And these expressions, they relate the individual items of the target document type to the source document type. And as this is the case, as these expressions relate these items to the source type, these expressions themselves might be regarded as metadata of these target items. And what now emerges is the insight that the complete transformation might very well be generated from a metadata tree, where the metadata are XPath expressions relating the individual items of the target format to the source form, target document type to the source document type. And I designed a generic metadata model for this purpose, which is described in the paper and which enables a semi-automatic code generation for affecting document transformations. So the first step is a generic transformation from XSD into an initial version of a metadata tree. This, of course, has also only placeholders, value placeholders for the metadata. Then the human steps in and he or she edits the metadata tree. And the result is an edited or final metadata tree. And then comes a second transformation step, again absolutely generic, which transforms the edited metadata tree to the final code affecting the transformation. All this is completely generic. So if you want to implement the transformation, you just perform these steps, and all you have to do as a human is edit the metadata tree. And this has been used for various web services, for the implementation of various web services, and the results have been really very satisfying. The benefits are, of course, first of all, significantly reduced human effort. And there's also the prospect of using the edited metadata tree as a single source in the future for multiple transformators in several programming languages, because the human work has there stopped and I just have to extend my code generator. Well, okay, time for wrapping up. Location trees are representations of document models, and they are implied by a schema. Location trees capture the schema content in a transformation-friendly way, and therefore they enable the development of interesting tools. And beyond that, location trees can be regarded as extensible document models, and they are well suited for extension by with non-schema information like facts and metadata. And last but not least, as location trees are XSD based, I think that XSD acquires a new potential as a data modeling language. Using location trees as a catalyst, moderate effort suffices to transform XSD into a growing range of valuable resources. Thanks.
Thank you, Hans. Any questions from the audience?
Hans-Jürgen, you started by talking about schema component models being a graph, and then you somehow magically converted this into a tree. And I missed the step as to how you handle recursive models.
Yeah, that's a very good question, because this is also one of the problems. So cyclic, there can be cycles. And it is no problem to represent this in the location tree. So it's described in the paper. So there are special attributes. There are two kinds of cycles. One are via group, via types, so that a descendant, an element has a type which an ancestor has, and it is via groups. And so there are special attributes representing this. So there is no problem representing this, but I skipped this, that concerning the data path, there is really an open question, because if you have such cycles, in fact, the data paths are infinite. So I think it would be very interesting to attempt future work somehow to find expressions which say like this path and then something similar to regular expressions, a fraction of this path fragment could repeat itself or something. But I have not yet. Pardon?
A finite representation.
Exactly, yeah. But I think this is very, very demanding, and I have not yet started anything. So, but my experience also, I work in practice really with document types which do have this, but my experience is in practice, it has not yet disturbed me, because these were very special corners of the big document. But it is one of the basic limitations or problems yet to be taken care of, yes.
Debbie.
Thank you very much. Is your schema diff up on your GitHub site?
Not yet, but let me also say what I showed is a very primitive schema diff. So I have written a much more elaborate one, which will then appear also on the GitHub side. Only I have to refactor it. The code now on GitHub is completely refactored, and I piece by piece add now all the things I wrote in the last years in the new version. But it will be my pleasure to send it to you.
Please do. Thank you. Finding a good schema diff is really tough. There's one out there by Chris Maloney, and it's dreadful. And Priscilla Walmsley wrote one that's actually quite good, but it's incredibly hard to use because it's totally undocumented. And we could really use a good one. Remember, I start in DTD land, so the first thing I have to do is make a schema, but that's easy. I've got rote code to do that. But getting a good schema diff would be very nice. Thank you.
Yeah, and in fact, I can also add to this, and this is one I had to limit the representation of how to use them. Schema diff was a candidate, and it's one of the great candidates, because the complex tool I use, it makes a parallel iteration about both trees, and then observes what I showed, just gives a difference in paths, but then it observes if everything is really equal in corresponding nodes, and then reports also the type differences, if, for example, the enum has changed at this point, and so on. So this is really one of the important use cases of location trees.
Well, I thank you. That's a tool we could all use.
Okay. I have one quick.
Have you considered, you know, pure visualization tools such as FreeMind or, you know, MindMap tool? Because those formats will be XML also. So it occurs to me that you could easily do transformations from your, well, let's say factories with different facets
Yeah.
of the same thing into mind maps interactively, and you could actually gain even, it would be even easier to explore differences in your models. This is really cool stuff.
I absolutely agree with you. There is a great potential, but I have myself not yet explored it. Yeah.
One last question, Michael.
One thing that struck me about your location trees was a strong similarity to that of Trojan's X-definition model for defining schemas. Have you compared and contrasted?
I can only say that I agree that there is a, let's say, the basic idea, there is this similarity, but I think it's also limited. So these X definitions are more geared upon creating applications, so to speak. And I'm close to the schema. And the first thing I want is to capture the schema and create this new starting point.
Okay.
Thank you very much, Hans.